The morning of March 1945 brought salvage crews to a site that would soon send ripples through Japan's aviation establishment. Floating in the cold waters off the Japanese coast, partially submerged but remarkably intact, sat an F4U Corsair. The distinctive inverted gull wings protruded from the water's surface like the skeleton of some great metallic bird. Within hours, naval personnel had secured lines to the wreckage, and the careful process of recovery began. This was not the first American aircraft to fall into Japanese hands. Throughout the war, salvage teams had recovered dozens of downed Allied planes from jungle battlefields and ocean crash sites. But this recovery was different. Most captures involved mangled wrecks, aircraft torn apart by gunfire or shattered by impact. This Corsair had suffered engine failure and ditched intact. The pilot had ejected cleanly. The fighter had settled into the water without the catastrophic structural damage that typically accompanied combat losses. As the salvage vessel towed the waterlogged fighter toward shore, word spread through Japan's technical intelligence community. The Yokosuka Naval Air Technical Arsenal received immediate notification. Engineers at the Army Aviation Technical Research Institute at Tachikawa were alerted. This was an opportunity that might not come again, a modern American frontline fighter, substantially intact, available for comprehensive examination. The Corsair represented everything Japanese pilots had learned to fear in the skies over the Pacific. Since its combat debut in 1943, this fighter had evolved from a troubled newcomer into one of the war's most dominant combat aircraft. Japanese pilots who survived encounters with Corsairs reported the same characteristics repeatedly: devastating speed, overwhelming firepower, and nearly indestructible construction. The fighter could absorb damage that would shred a zero and keep flying. It could outdive and outclimb anything in the Komintele, Japanese arsenal. In the hands of a skilled pilot, employing proper tactics, the Corsair was nearly untouchable. But combat observations provided only partial understanding. Pilots could describe what the Corsair did, not how it accomplished these feats. They could report its performance, not the engineering that enabled such capabilities. Only physical examination could reveal the secrets of American aviation technology, the materials, manufacturing techniques, and design philosophies that created such a formidable weapon. The Corsair that arrived at Yokosuka Naval Air Arsenal bore the scars of its water landing. Salt corrosion had begun attacking exposed metal surfaces. Water had penetrated the cockpit and fuselage. The massive Pratt Whitney engine would require complete disassembly and cleaning, but the fundamental structure remained sound. The wings, though waterlogged, showed no buckling or fractures. The fuselage retained its shape. The landing gear, though likely damaged by the ditching, could be examined for its engineering. This was as close to a pristine example as Japanese engineers could hope to obtain under wartime conditions. Initial procedures followed established protocols. Security personnel cordoned the examination area. Photographers documented the aircraft from every angle before technicians touched anything. Measurements began immediately: wingspan, length, height, every external dimension carefully recorded. The distinctive inverted gull wing drew immediate attention. Japanese designers understood the theoretical advantages of this configuration, but seeing it implemented successfully highlighted the gulf between understanding a concept and executing it with sufficient precision to make it work. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The examination team assembled at Yokosuka represented Japan's aviation elite. These were not novices or enthusiasts, but trained engineers with years of aircraft design experience. Many had worked on Japan's own fighter programs. They understood aerodynamics, structures, and power plants at the highest technical level. Their professional competence made what they were about to discover all the more significant. These were experts examining the work of their American counterparts, and they would soon confront truths about the state of their own industry that were impossible to ignore. As teams began carefully removing panels and access covers, the systematic dissection of the Corsair commenced. Every component would be examined, measured, photographed, and assessed. The goal was comprehensive understanding, not just what made the Corsair effective, but how American industry achieved such results. The engineering, the manufacturing, the quality control, the materials science, every aspect would be scrutinized. What Japanese engineers did not yet fully grasp was that this examination would serve less as intelligence gathering for future combat than as a final reckoning with technological reality. By March 1945, Japan's strategic position was catastrophic. American B-29s were incinerating Japanese cities with impunity. The Navy had been destroyed as an effective fighting force. The Philippines had been liberated. Iwo Jima had fallen after horrific fighting, bringing American air bases within easy range of the home islands. Okinawa would soon come under assault. In this desperate context, the Corsair examination would take on significance beyond tactical intelligence. It would become a mirror reflecting Japan's industrial limitations and America's technological superiority. The engineers at Yokosuka were about to conduct not just a technical analysis, but an autopsy of their own nation's failed attempt to match American industrial might. The work began in the spring of 1945, as Japan's war effort collapsed. But for the technical personnel at Yokosuka, the broader strategic situation faded into background noise. Before them sat a puzzle of aluminum, steel, and innovation. Their task was to solve it, to understand it, to learn from it. What they would discover would exceed even their most pessimistic estimates of the technological gap separating Japanese and American aviation. The Corsair was about to teach lessons that Japanese engineers would never forget. The disassembly proceeded with methodical care. Each component removed from the Corsair revealed new layers of American engineering sophistication. Japanese technicians approached the work with professional detachment, but as examination progressed, that detachment gave way to growing recognition of just how far American aviation technology had advanced. The wing structure commanded immediate attention. Removing the fabric covering from the outer wing sections, a design choice that initially puzzled Japanese engineers exposed the internal skeleton. What they found was simultaneously familiar and alien. The fundamental principles of wing construction were universal, but the execution demonstrated manufacturing capabilities that seemed almost incomprehensible. The main wing spar was a massive forging, the primary load-bearing structure that carried all flight stresses. Japanese engineers understood spar design intimately. Every aircraft they had ever worked on depended on similar structural elements. But this spar was different. The size, the precision, the material quality, everything indicated manufacturing processes operating at levels Japanese industry struggled to achieve. American metallurgists had produced aluminum alloy forgings with strength characteristics Japanese facilities could not consistently match. The spar's cross-section showed uniform grain structure, indicating proper heat treatment and quality control throughout the forging process. Load calculations revealed strength margins that Japanese designers would have considered excessive until they recognized that these margins enabled the Corsair to survive battle damage and high-G combat maneuvers that would destroy aircraft with less robust construction. The wing's internal structure told a similar story. Stamped aluminum ribs, dozens of them, showed remarkable consistency. Each rib was virtually identical to the next. In Japanese aircraft production, especially by 1945, such consistency had become increasingly difficult to maintain. Individual aircraft showed variations in component quality, as material shortages forced the use of substitute alloys, as experienced workers were conscripted for military service, as factories operated under constant threat of American air raids. The Corsair's ribs weren't just consistent, they were beautifully made. Surface finishes were smooth and professional. Lightening holes were precisely located and cleanly formed. Every bend, every flange, every mounting point reflected manufacturing processes with tight quality control. This wasn't the work of struggling factories using substitute materials and inexperienced workers. This was mature industrial production operating at peak efficiency. Attention shifted to the armament installation. 6 Browning AN-M2, .50 caliber machine guns represented firepower that far exceeded anything in Japanese fighters. But what struck Japanese examiners wasn't just the number of guns, it was the system's completeness and sophistication. The installation was compact, efficient, and designed for maintenance under combat conditions. Ammunition boxes fed cartridges through precisely engineered linkages. Spent cartridge ejection systems prevented jams. Charging mechanisms were accessible and reliable. The guns themselves were masterpieces of precision manufacturing. American ordnance production had achieved reliability levels that seemed almost magical to Japanese technicians. The Browning M2 was a mature design, perfected through decades of development and manufactured by the millions with extraordinary consistency. Japanese attempts to produce comparable weapons had largely failed to achieve similar reliability. Japanese machine guns, even when new, experienced higher rates of malfunction. Under combat stress and inadequate maintenance, reliability deteriorated further. Examining the Browning guns revealed manufacturing techniques that explained their legendary reliability. Tolerances were measured in thousandths of an inch. Moving parts fit together with precision that minimized friction and wear. Surface finishes on critical components showed careful attention to detail. Every gun examined appeared capable of firing thousands of rounds without malfunction. Japanese ordnance, by contrast, struggled with consistency. Even the best Japanese machine guns required more frequent maintenance and suffered higher failure rates. The discovery of armor protection throughout the Corsair's structure provided another revelation. 150 pounds of armor plate protected the cockpit. A 1.5-inch thick bulletproof glass panel sat behind the windscreen. Self-sealing fuel tanks incorporated multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss. The entire aircraft was designed around pilot survivability. Japanese fighters had largely abandoned such protection in favor of lighter weight and better maneuverability. The Zero's early success seemed to validate this philosophy. Superior agility could help avoid being hit, but as American fighters grew more powerful and better armed, the lack of protection became fatal. Japanese pilots increasingly flew aircraft that burned easily when hit and provided no protection against enemy fire. The Corsair demonstrated that proper engineering could incorporate substantial protective armor without sacrificing performance. The key was the massive power of the R-2800 engine, enough power to overcome the weight penalty of armor, while still delivering superior performance. This represented a fundamental difference in design philosophy. Japanese designers optimized for performance through weight reduction. American designers achieved performance through overwhelming power, then added protection that kept pilots alive. The electrical and hydraulic systems throughout the aircraft revealed similar patterns. Wiring was properly insulated, organized, and routed. Hydraulic lines were precision manufactured with high-quality fittings. The landing gear mechanism was complex but precisely made, engineered to withstand thousands of carrier landings. The cockpit instrument panel presented comprehensive arrays of gauges and controls that far exceeded anything in Japanese fighters. Every system reflected attention to detail and manufacturing quality. Perhaps most revealing was examining components that seemed mundane: fasteners, brackets, access panels, control linkages. Even these routine items showed consistent quality. Hardware was properly manufactured with correct dimensions and finishes. Nothing felt improvised or makeshift. The entire aircraft exuded an aura of solid, professional construction. It felt substantial, built to last, engineered to survive combat and continue fighting. This overall quality stood in painful contrast to Japanese aircraft production in 1945. Wartime shortages had forced increasing use of substitute materials. Aluminum quality had deteriorated as supplies dwindled. Steel components showed inconsistent heat treatment. Surface finishes were rougher. Quality control suffered as production schedules demanded quantity over quality. Japanese aircraft by 1945 were still functional, still dangerous in the right hands, but they lacked the robustness and refined engineering evident in every aspect of the Corsair's construction. As examination of the airframe neared completion, Japanese engineers compiled their findings. The reports were technical, detailed, and professional, but underlying the dry language of engineering specifications was an unavoidable conclusion. American aviation technology exceeded Japanese capabilities across nearly every parameter examined. This wasn't a small gap that could be closed with focused effort. This represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. If the Corsair's airframe demonstrated American engineering excellence, the Pratt Whitney R-2800 double-wasp engine represented something approaching mechanical perfection. As Japanese technicians began the painstaking process of disassembling this power plant, they confronted the heart of American aviation superiority, the ability to produce reliable, powerful engines in quantities that seemed almost impossible. The R-2800 dominated the engine bay, a massive 18-cylinder radial arranged in 2 rows of 9 cylinders, displacing 2,800 cubic inches and producing over 2,000 horsepower. This engine delivered nearly double the power of most Japanese radial engines, but raw power told only part of the story. What truly impressed Japanese engineers was that the R-2800 actually produced its rated horsepower consistently, reliably, for hundreds of hours between major overhauls. Japanese engines, even new examples fresh from the factory, often failed to achieve their theoretical power ratings. Design specifications promised certain performance, but manufacturing limitations meant actual engines frequently underperformed. Worse, Japanese engines required constant maintenance. Hours between overhauls were measured in dozens or low hundreds, not the many hundreds of hours American engines routinely achieved. Combat units struggled with engine reliability issues throughout the war. The R-2800's construction revealed why American engines performed so much better. Removing the cylinder banks exposed internal components that represented manufacturing at levels Japanese facilities could not match. Cylinders were precisely machined with tolerances measured in thousandths of an inch. Each cylinder was virtually identical to the next, consistent bore dimensions, consistent wall thickness, consistent surface finish. This precision wasn't accidental. It resulted from sophisticated machine tools operated by skilled workers following rigorous quality control protocols. Pistons showed similar precision. Each piston was machined to exact specifications, with piston rings that seated properly and seals that minimized oil consumption. Connecting rods were forged and machined to tight tolerances, with bearing surfaces finished to mirror-like smoothness. The crankshaft was a masterpiece of metallurgy, a massive forging, properly heat-treated for strength and durability, with bearing journals finished to precision specifications. Japanese engine manufacturers understood these principles. They knew that precision manufacturing led to better performance, reliability. But knowing what should be done and possessing the industrial capability to do it consistently were entirely different matters. By 1945, Japanese engine production struggled with basic consistency. Material quality varied. Machining precision suffered as tool wear exceeded replacement capacity. Quality control deteriorated as production pressure mounted. The R-2800's two-stage supercharger system proved particularly revealing. This complex assembly maintained engine power at high altitudes by compressing intake air through 2 stages of compression. The supercharger incorporated intricate internal passages, precisely fitted rotating components, and sophisticated drive mechanisms. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Disassembling the supercharger revealed engineering that seemed almost magical. Internal clearances were measured in thousandths of an inch. Rotating components spun on precision. Bearings with surfaces finished to standards Japanese manufacturers struggled to achieve. The entire assembly had to operate at high speeds under extreme temperatures while maintaining precise alignment and minimal friction. That American manufacturers could produce such components reliably, in quantity, demonstrated industrial capabilities that far exceeded Japanese capacity. The engine's accessory systems told similar stories. Magnetos provided ignition timing with precision. Japanese electrical components couldn't match. The carburetor metered fuel with accuracy that ensured consistent power delivery. Oil pumps circulated lubricant with reliability that minimized wear. Every accessory, every subsystem, reflected manufacturing sophistication and quality control that Japanese industry envied but could not replicate. Perhaps most impressive was the overall integration. The R-2800 wasn't just a collection of well-made components, it was a system engineered to work as a unified whole. Every part supported every other part. The engine was designed for maintenance, with accessible inspection points and serviceable components. It was designed for reliability, with redundant systems and robust construction. It was designed for production, with components that could be manufactured consistently in quantity. Japanese engineers examining the R-2800 understood they were looking at the product of decades of American aero engine development. Pratt Whitney had been producing radial engines since the 1922. Each generation of engines incorporated lessons learned from previous designs. Manufacturing processes improved continuously. Quality control became more sophisticated. The R-2800 represented the culmination of this evolutionary development, mature technology, executed with precision and produced with consistency. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now, back to the story. The Hamilton, standard hydromatic propeller attached to the engine, proved equally instructive. At 13 feet 4 inches in diameter, this was the largest propeller ever fitted to a fighter aircraft. The variable pitch mechanism allowed the pilot to adjust blade angle for optimal performance during different flight regimes: fine pitch for takeoff and landing, coarse pitch for high-speed cruise. This controllability enhanced the Corsair's versatility and performance. Japanese engineers understood propeller theory. They knew that variable pitch propellers offered advantages over fixed pitch designs, but manufacturing large propellers with necessary precision exceeded Japanese capabilities. The Hamilton standard propeller's blades showed complex airfoil sections that varied from root to tip, optimized for efficiency across the blade's length. The pitch change mechanism incorporated precise hydraulic controls and robust construction that operated reliably under combat stresses. As examination of the power plant concluded, Japanese engineers compiled technical reports documenting their findings. The language remained professional and objective, but certain conclusions were inescapable. The R-2800 engine represented manufacturing sophistication and quality control that Japanese industry could not match. The gap wasn't simply about design knowledge. Japanese engineers understood engine design theory as well as their American counterparts. The gap was industrial capacity, manufacturing precision, quality control systems, material science, and accumulated expertise in production engineering. By the time these reports were completed, Japan's strategic situation had deteriorated beyond recovery. The examination of the captured Corsair occurred against a backdrop of national collapse. American B-29s were systematically destroying Japanese cities through conventional and incendiary bombing. The Navy had ceased to exist as an effective fighting force. The Army was preparing for homeland defense against inevitable invasion. In this context, the technical reports on the Corsair took on somber significance. This was not intelligence gathering for future victories. There would be no future victories. This was a final accounting, a reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa had documented the full magnitude of American industrial and technological superiority. Their reports would survive the war's end, discovered by American occupation forces, and eventually archived as historical records. These documents serve as testament to a moment when one nation's engineers confronted another nation's capabilities and recognized the vast chasm separating them. The examination of the F4U Corsair, particularly its revolutionary 2,000 horsepower engine, represented Japanese aviation's acknowledgement that they had been fighting an opponent whose industrial capacity and technological sophistication exceeded anything they could match. The lessons were harsh but clear. Superior technology, backed by massive industrial capacity and sophisticated manufacturing, had overcome courage and skill. The R-2800 engine producing reliable power that Japanese engines could not match, manufactured with precision Japanese factories could not achieve. Available in quantities Japanese industry could not imagine symbolized everything about American power that had proven overwhelming. Japanese engineers would remember these lessons. In the post-war period, as Japan rebuilt its industrial base, the emphasis on quality, precision, manufacturing, and continuous improvement that would characterize modern Japanese industry had roots in the hard truths learned when Japanese engineers examined what American industry could produce. The examination of the Corsair and its remarkable engine had taught lessons that would shape Japanese manufacturing philosophy for generations to come. The technical reports compiled by Japanese engineers at Yokosuka Naval Air Technical Arsenal in the spring of 1945 represented more than dry assessments of American aviation technology. They were confessions written in the language of engineering specifications, admissions of industrial inadequacy disguised as objective analysis. As these documents circulated through what remained of Japan's military aviation establishment, they confirmed what many had suspected but few had been willing to acknowledge openly. Japan had been fighting a war it could never win. The timing of the Corsair examination added tragic irony to the enterprise. By March and April 1945, when Japanese technicians were measuring wing spars and disassembling the R-2800 engine, Japan's strategic position had deteriorated beyond any possibility of recovery. The Imperial Japanese Navy had been effectively destroyed at the Battle of Leyte Gulf in October 1944. The Philippines, once considered a critical defensive perimeter, had been liberated by American forces. Iwo Jima had fallen in March, after 36 days of brutal fighting that cost nearly 7,000 American lives but placed B-29 bomber bases within 660 miles of Tokyo. As Japanese engineers examined the Corsair's sophisticated manufacturing, American B-29 superfortresses were systematically incinerating Japanese cities. The firebombing of Tokyo on the night of March 9–10, 1945, killed an estimated 100,000 civilians and destroyed 16 square miles of the city. Similar raids targeted Nagoya, Osaka, Kobe, and dozens of other urban centers. Japan's industrial capacity, already strained beyond breaking by years of war, was being methodically destroyed from the air. The invasion of Okinawa began on the 1st of April 1945, as Japanese technicians continued their examination of the captured fighter. This battle would become the bloodiest of the Pacific War, with over 12,000 American and 100,000 Japanese military deaths, plus perhaps 100,000 Okinawan civilian casualties. Okinawa's fall was inevitable. American material superiority. It was simply overwhelming. Japanese forces fought with desperate courage, employing kamikaze tactics that achieved tactical successes, but could not alter strategic reality. In this context of national catastrophe, the Corsair examination became an exercise in documenting defeat. Every measurement taken, every component analyzed, every manufacturing technique assessed, reinforced the same brutal conclusion. American industrial capacity exceeded Japanese capabilities by margins so vast that no amount of courage, skill, or tactical brilliance could compensate. The war had been lost not on battlefields but in factories, not through failures of will but through limitations of industrial capacity. Evidence suggests Japanese technicians made serious efforts to repair the captured Corsair toward flying condition. Photographs discovered after the war show captured Corsairs with patched wings and fuselages, indicating attempts at restoration. Whether actual flight testing occurred remains uncertain. Records from this chaotic period are incomplete and contradictory, but the repair attempts themselves reveal the seriousness with which Japanese aviation authorities viewed this intelligence opportunity. Flying the Corsair would have provided invaluable data beyond what static examination could reveal. Performance testing could have documented acceleration, climb rate, turning performance, and handling characteristics under various conditions. Japanese test pilots could have evaluated the aircraft's strengths and weaknesses firsthand, developing tactics to counter it more effectively. But by April and May 1945, such intelligence had become largely academic. There were fewer Japanese pilots capable of employing new tactics, fewer aircraft to employ them with, and less fuel to power any operations. The broader context of Japan's technical intelligence efforts during the war reveals a consistent pattern. Japanese engineers captured and examined numerous Allied aircraft. Throughout the conflict, American P-40 Warhawks, P-38 Lightnings, B-17 bombers, British Hurricanes and Spitfires, even Soviet fighters captured during border clashes. Each examination provided valuable intelligence about Allied capabilities and manufacturing techniques. But intelligence alone could not overcome industrial limitations. Japanese engineers knew, for example, that American aircraft featured superior armor protection, self-sealing fuel tanks, and more powerful engines. They understood the advantages these features provided, but knowing what should be done and possessing the industrial capacity to implement it were entirely different challenges. Japan's industrial base, smaller to begin with than America's, operated under severe resource constraints. Aluminum was scarce, high-quality steel was limited, aviation fuel was increasingly unavailable, skilled workers were being conscripted for military service faster than they could be replaced. The examination of the Corsair's R-2800 engine particularly highlighted these constraints. Japanese engineers could disassemble the engine, measure every component, document every manufacturing technique, and understand exactly how it achieved such remarkable performance and reliability. But that knowledge was useless without the industrial infrastructure to implement it. Producing engines with similar precision required sophisticated machine tools Japan no longer possessed in sufficient numbers. It required quality control systems that Japanese factories, operating under wartime pressures, could not maintain. It required materials of consistent quality that Japan's strained supply chains could not deliver. Perhaps most fundamentally, it required time to develop new manufacturing processes, time to train workers, time to establish quality control protocols, time to debug production problems. Japan had run out of time in 1942, though few recognized it then. By 1945, the truth was inescapable. The war was over. Only the final terrible accounting remained. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japanese technical intelligence efforts. Captured Allied aircraft were scattered around the facility in various states of disassembly. Technical reports, engineering drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected these materials, recognizing their value for understanding what Japan had learned during the war. The captured Corsair itself likely ended up scrapped during the chaotic post-war period. Most Japanese military equipment was destroyed by American occupation authorities to prevent any possibility of renewed militarism. The aircraft that had traveled so far from Chance Vaught's Connecticut factory to combat operations over the Pacific, from emergency ditching to Japanese salvage, from waterlogged wreck to technical examination, probably ended its existence in a scrapyard, reduced to aluminum ingots with no memory of the lessons it had taught. But those lessons survived in the reports Japanese engineers had compiled. These documents, discovered by American occupation forces and eventually archived in military intelligence repositories, provide remarkable insights into Japanese technical capabilities and limitations during the war's final months. They reveal engineers who understood their profession thoroughly, who could recognize excellence when they saw it, and who were honest enough to document their own nation's shortcomings. The tone of these reports is striking. There is no defensiveness, no attempt to minimize American achievements or exaggerate Japanese capabilities. The assessments are professional, objective, almost clinical. Japanese engineers documented what they found with the same precision they would use for any technical analysis. The reports acknowledge superior American manufacturing without editorializing. They describe advanced materials and techniques without making excuses for why Japanese industry could not replicate them. This professional honesty perhaps reflects the engineers' understanding that by the time they were writing these reports, the war's outcome was no longer in doubt. There was no strategic value in deception or wishful thinking. The task was simply to document reality as accurately as possible, creating records that might prove valuable in whatever future awaited Japan after defeat. The examination of the F4U Corsair by Japanese engineers in 1945 stands as one of history's more poignant episodes, a moment when technical professionals on the losing side confronted the full magnitude of their opponent's superiority. Unlike combat pilots who saw only what enemy aircraft could do in battle, these engineers saw how American industry achieved such results. They examined the manufacturing precision, the material quality, the sophisticated design, and the attention to detail that characterized American aviation technology. More importantly, they recognized that these advantages were not temporary or easily overcome. They represented fundamental differences in industrial capacity, resource availability, manufacturing sophistication, and accumulated engineering expertise. Japan had entered the war, hoping that tactical brilliance and fighting spirit could compensate for material disadvantages. The examination of the Corsair confirmed what battlefield results had already demonstrated. Modern warfare was ultimately decided by industrial capacity, and in that contest, Japan had been hopelessly outmatched from the beginning. The legacy of this examination extended far beyond the war itself. In the post-war period, as Japan rebuilt under American occupation, Japanese engineers and industrialists applied lessons learned from examining American technology. The emphasis on quality control, precision manufacturing, continuous improvement, and attention to detail that would characterize Japan's post-war industrial renaissance had roots in the hard truths learned during the war. Japanese engineers who had examined the Corsair and other American equipment understood that matching American quality required systematic attention to manufacturing processes, worker training, quality control, and continuous refinement. These principles, learned through painful wartime experience, became foundational to Japanese manufacturing philosophy in subsequent decades. The nation that had been unable to match American manufacturing precision during the war would eventually become renowned worldwide for manufacturing excellence. The story of the captured Corsair thus ends not with the aircraft's likely destruction in a post-war scrapyard, but with the survival of lessons it taught. Japanese engineers who examined this fighter learned truths about manufacturing, quality, and industrial capacity that shaped their nation's future. The examination reports, archived and largely forgotten, serve as historical testimony to a moment when one nation's engineers confronted another's capabilities and honestly documented what they found. The F4U Corsair that Japanese salvage crews recovered in early 1945 was just one aircraft among thousands produced by American factories. But for the Japanese engineers who examined it, this single fighter represented the full measure of American industrial power. Every precisely machined component, every consistently manufactured part, every sophisticated system told the same story. Japan had been fighting an opponent whose industrial capabilities exceeded anything Japanese industry could match. It was a lesson written in aluminum alloys and precision tolerances, taught by an enemy's engineering excellence, learned too late to change the war's outcome, but remembered long enough to shape the peace that followed. The examination of the Corsair stands as testament to the moment when Japan's aviation establishment confronted technological reality and, with professional honesty, admitted they had never seen anything quite like what American industry could produce. The technical reports on the captured Corsair, compiled during Japan's final months of desperation, would ultimately prove more valuable than their authors could have imagined, not as military intelligence, but as historical documentation of a technological awakening. These documents, discovered by American occupation forces and filed away in military archives, captured a unique moment, the precise instant when Japanese engineers fully comprehended the industrial chasm separating their nation from the United States. What makes these reports particularly valuable to historians is their unflinching honesty, written as Japan faced annihilation, with American bombers reducing cities to ash and invasion fleets gathering for the final assault. These documents contained no propaganda, no face-saving rhetoric, no appeals to fighting spirit overcoming material disadvantage. They were engineering assessments, pure and technical, documenting capabilities Japanese industry could not match, and manufacturing precision Japanese factories could not achieve. The psychological impact on the engineers themselves remains largely undocumented. These were men who had devoted their careers to Japanese aviation, who had designed fighters and bombers, who understood their profession at the highest level. Examining the Corsair forced them to confront uncomfortable truths about their own work. Every precisely machined component, every consistently manufactured part, every sophisticated system represented standards they had strived for but never fully achieved. Consider the position of a senior engineer at Yokosuka, who had spent years developing Japanese fighter designs. This individual would have understood aerodynamics, structures, and power plants as well as any engineer anywhere. He would have worked within the constraints available: limited aluminum supplies, inconsistent material quality, inadequate machine tools, shortages of skilled workers. He would have done his best with available resources, and now, examining the Corsair, he confronted what was possible when those constraints didn't exist, when engineers had access to unlimited resources, sophisticated manufacturing, and industrial capacity beyond imagination. The emotional weight of such realization goes unrecorded in technical reports, but it must have been substantial. These engineers had not failed due to lack of knowledge or effort. They had been trapped by circumstances beyond their control: resource limitations, industrial capacity constraints, and a war economy stretched beyond breaking. The Corsair demonstrated what Japanese engineers might have achieved if they had possessed American resources and manufacturing capabilities. It was a glimpse of a parallel world where Japanese industry matched American capacity. The post-war period brought profound changes to Japanese aviation and industry. The American occupation initially prohibited all aircraft production and research. Japanese engineers who had spent their careers developing military aircraft suddenly found themselves without purpose. Facilities like Yokosuka Naval Air Technical Arsenal were repurposed or dismantled. The aviation industry that had employed tens of thousands essentially ceased to exist, but knowledge survived even when industry did not. Engineers who had examined American equipment during the war remembered lessons about quality control, precision manufacturing, and systematic approach to production. As Japan rebuilt during the 1950 seconds and 1960 seconds, these principles found new application in civilian industries. The automotive sector, electronics, manufacturing, and precision machinery production all benefited from expertise developed during the aviation era. The philosophy that emerged: continuous improvement, attention to detail, worker involvement in quality control, systematic problem-solving had roots in wartime lessons. Japanese engineers had learned from examining American technology that quality came from systematic processes, not just skilled individuals. Manufacturing excellence required attention to every detail, from raw material specifications to final inspection protocols. These insights, learned through painful wartime experience, became foundational to Japan's post-war industrial philosophy. Ironically, the nation that had been unable to match American manufacturing during the war eventually became synonymous with quality manufacturing. By the 1970 seconds and 1980 seconds, Japanese automobiles, electronics, and machinery had earned worldwide reputations for reliability and precision. The transformation from wartime inadequacy to peacetime excellence took decades and involved factors far beyond aviation technology. But the underlying principles: systematic quality control, continuous improvement, precision manufacturing reflected lessons learned when Japanese engineers examined what American industry could produce. The Corsair itself enjoyed remarkable longevity for a World War II fighter design. Production continued after the war ended, with the final Corsair rolling off Chance Vaught's assembly line in December 1952. Total production reached 12,571 aircraft across all variants, making it one of the longest production runs of any piston-engine fighter. The design proved adaptable enough to remain effective into the jet age, serving primarily in ground attack roles where its rugged construction and heavy payload capacity remained valuable. During the Korean War, Corsairs flew thousands of combat sorties. Navy and Marine squadrons used them extensively for close air support, interdiction, and armed reconnaissance. The aircraft that had terrorized Japanese pilots over the Pacific now supported United Nations forces against North Korean and Chinese troops. Its ability to absorb ground fire and continue operating from rough forward airfields made it invaluable, despite being technologically obsolete compared to emerging jet fighters. Foreign air forces continued operating Corsairs long after American forces retired them. France flew Corsairs in Indochina and Algeria through the 1950s and early 1960s. The aircraft's rugged reliability and heavy armament suited counterinsurgency operations where sophisticated performance mattered less than durability and firepower. Honduras and El Salvador both operated Corsairs into the late 1960s, leading to the surreal situation where the type's final combat missions involved Corsairs fighting other Corsairs during the 1969 Soccer War. The last combat victories credited to Corsairs occurred on the 17th of July 1969, when Honduran Captain Fernando Soto shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. This final combat, nearly 30 years after the prototype's first flight, demonstrated the fundamental soundness of the original design. The engineering excellence that Japanese technicians had documented in 1945 remained evident decades later in aircraft still flying combat missions. Today, the story of Japanese engineers examining a captured Corsair survives primarily in archives and historical accounts. The technical reports compiled at Yokosuka rest in repositories, occasionally consulted by historians researching wartime intelligence operations or Japanese aviation technology. The aircraft itself vanished long ago, almost certainly scrapped during the chaotic post-war period. No physical trace remains of the specific fighter that taught such profound lessons, but the lessons themselves endure. They survive in understanding how technological and industrial advantages shape warfare outcomes. They survive in recognition that courage and skill, however admirable, cannot overcome vast material disparities. They survive in appreciation for the engineering excellence that characterized American wartime production. And perhaps most significantly, they survive in the transformation of Japanese manufacturing from wartime inadequacy to post-war excellence, a transformation rooted partly in hard truths learned when Japanese engineers examined an American fighter and admitted they had never built anything quite like it. The examination of the F4U Corsair stands as testament to a moment when technological reality became unavoidable, when professional honesty compelled acknowledgement of capabilities beyond reach, and when lessons learned in defeat ultimately contributed to peacetime success. It remains a story worth remembering not for triumphalism or schadenfreude, but for what it reveals about technology, industry, warfare, and the complex pathways through which knowledge travels across time and between nations.